Hello everyone, I'm back. This is the second video in our chemical engineering teaching series. So yesterday I talked about mass and energy balances, or just mass balances in general. I kind of gave an introduction to a general balance, and then I talked a little bit more about how to actually set up a mass balance. If you are interested in that video and you haven't watched it yet, I'll put a card up right now so that you can actually click on that and watch that for yourself. But today I wanted to give an introduction to energy balances. And hopefully that'll give you a sense of how we set up energy balances, as well as how we can actually solve some problems with it. So I'll do an example at the end as well. All right, so with that, let's jump straight into it. Remember, our overall balance is accumulation equals in minus out plus generation minus consumption. This was mentioned in the last video, so if you want to watch that, again, the card's there, and I will also put the link to that video in the description below. Now, we're talking about energy today. So there's one law that's very important here, which is the conservation of energy. Now, conservation of energy tells us that energy cannot be created or destroyed. It can only be transferred from one form to the other. So we can convert potential to kinetic or kinetic to potential, but we can't just suddenly destroy energy or create energy, with the exception if we're doing some like nuclear energy balances, which you probably won't as a chemical engineer. So we can actually get rid of this generation consumption term, and our energy balance becomes accumulation equals in minus out. So pretty nice. All we have to do is make sure that we just account for all the different types of energy that are in our system. So that's why the energy balance seems so fleshed out. So let's actually define some of the terms that we're going to actually use in this energy balance, because I don't want to assume that you guys know all the terms already. So we'll start first with, of course, U. And what U is, this is the internal energy of the system, right? So it's a relative energy state essentially. So if you have energy state U of something joules, that's it. That tells you what the energy state of the system is. The other thing we also want to know is H. This is the internal enthalpy of the system, not to be confused with U. Right now, you might think, okay, H and U, they seem pretty similar. Like, what's the actual difference here? Well, the difference that people forget often is that U and H are actually related, right? And this is not a thermo course per se, so I will make a separate video about the thermo and where this kind of comes from. But essentially, the enthalpy is equal to the internal energy of the system plus the work done by the fluid. So this is fluid work, PV. So you can imagine this as flow work, right? Uh, this is the reason we make this distinction, right? Is so that we're going to have terms with U and we're going to have terms with H, and it's important to know the difference between the two. Um, so that's why that's there. Next, we have Q. Now Q is the rate, or yes, Q dot would be the rate, but Q is a representative of heat transfer. Q dot is heat transfer. And there's one term that all chemies should know, and that's adiabatic. And adiabatic just simply means that Q dot equals 0 for the system. Next, we have shaft work, which is work done on the system that's not fluid work, right? So besides the work of fluid moving from one point to another, this is the shaft work. So think about this as like a turbine, right? If I am And another thing that's important with shaft work is to determine the signs. Depending on which field you're in, they have different signs, whether positive or negative. If you're in physics, they have a different convention than when we were in chemical engineering. But for chemical engineering, the important thing is if I'm doing work to the system, that is considered positive energy. I'm adding work to the system or adding energy to the system, right? So this would be, okay, you're heating something on a stove and then you're mixing it, right? That's a form of shaft work. So positive Ws is equal to add energy to the system. And conversely, negative shaft work would be you're extracting energy from the system. So in other words, okay, the fluid is moving and it's turning a turbine. Well, that turbine is taking energy out of the system. So that is negative shaft work. And then lastly, I'll denote kinetic energy and potential energy with Ke and Pe respectively. So those are all our terms. And so now we can actually write the full energy balance, right? So we have accumulation, du dt, is equal to all the energy coming in. So this is Q plus shaft work in. We also have any streams coming in, like if we have mass flowing in, that has an enthalpy that we need to account for. We also have a kinetic energy in and a potential energy in. So you can see here that we are already incorporating both U and H in here. So that's the reason why I said that they're different, right? This is the reason why this work is work shaft. It's shaft work. The H in accounts for the flow work. And then we subtract what's out. So mass out, H out, kinetic energy out, potential energy out. And this is it. This is the full balance. Well, maybe you have some other form of energy as well in the system. Maybe you have some electrical energy or something like that. Um, and if so, like, obviously that's an important thing to keep in mind, right? But this in general will be the form that you use for all the problems that you use. It's just a matter of canceling out terms. Now, this is generic for an open system. And when I mean open system, right, I mean something that looks like this. So you have Q and work, but you also have mass coming in and mass coming out. There's another type of system that is closed. And there's no mass coming in or out, but you might have Q and shaft work. Closed systems are nice because you don't have anything coming in or out, the system just becomes du dt equals Q plus shaft work. So very nice, very easy. Closed systems are nice. Anyway, that's a general overview. So let's start by going through a practice problem. So we have a turbine. Hopefully that looks like a turbine to you. We have some mass in. That's at 400 C and 1 megapascal. And it comes out saturated at 10 kilopascals. This turbine extracts 500 kilowatts of shaft work. And the question is, what is the mass flow rate? So what's m dot? So we'll start by setting up the balance. Du dt equals Q plus shaft work plus mass in, which is same as mass out, where mass balance is steady, minus mass out. And honestly, I can just get rid of these sigmas because there's only one species coming in, and that's steam. And then there's no change in kinetic energy or potential energy, so I'm just going to leave those out as well. And this is our total balance. Oh, one thing I forgot to mention about the problem. My bad. This is an adiabatic system, so we're assuming Q is equal to 0. So that gets canceled. We're at steady state, du dt gets canceled. And so our balance becomes 0 equals shaft work plus mass in times the difference between H in and H out. Now, H in and H out, these are values you would get from a steam table. This is not a video about, how to search up steam tables. So I'm just going to give you those values here right now. So H in is equal to 3,264 joules per gram. And H out is equal to 2,584 joules per gram. So now we should be able to solve this. So we have 0 is equal to, I'm going to convert this to joules to make everything easy. 500 kilojoules per second. There's 1,000 joules in 1 kilojoule. Plus the mass flow rate times 3264 minus 2584. This is joules per gram. And so now we just solve for the mass flow rate, which is mass flow rate is equal to 500 times 10 to the 3. This should be a negative because we are extracting energy from the system, right? The turbine is producing work. We're removing energy from the system, so it's negative. 3264 minus 2584. This is joules per second, joules per gram. And so when we do this, 735 grams per second. That's it. Anyways, that's it for this video. Hopefully this helped you and gave you a general sense of how to set up an energy balance. Again, if you have any questions, feel free to drop it in the comments. I'll keep an eye out and try to answer them the best I can. Alrighty, best of luck, and I'll see you in the net tomorrow.